Good morning, all of you. Welcome to C. Jain's Rank Zone. Today we are going to start new chapter, that is hydrogen and its compounds, hydrogen and its compounds. From this chapter also, you'll expect a couple of questions for entrance examination. So please listen carefully. Now we are going to start hydrogen and its compounds. Yes, this is called hydrogen and its compounds. First, coming to introduction part of hydrogen and its compounds. Hydrogen is the most abundant element in the universe and the third most abundant element on the surface of the earth. Why it is abundant element in the universe? Because all the stars, all the stars are made up of third most abundant element in the universe because on the surface of the earth, and the abundant element in the universe because all the stars are made up of hydrogen and helium. All the stars, all the stars are made up of hydrogen and helium. And in the universe, as we already know, the stars are more when compared to the Earth because Earth is only a tiny speck in the universe. So that's why hydrogen is the most abundant element in the universe and third most abundant element on the Earth's surface of the Earth. That is Earth crust. It's the simplest element with only one electron in its orbit around the nucleus containing only one proton. It is not containing, it is containing only one proton. So hydrogen consisting of one electron and one proton. It exists as a diatomic molecule, that is H2. H2 in a sense like this indicate. It exists as hydrogen exists as diatomic molecule in its elemental form. Hydrogen atom does not exist, only hydrogen molecule exists in the nature. The global concern related to clean energy makes it so important to study hydrogen separately from other elements. This concern can be overcome to a greater extent by the use of hydrogen as a source of energy. So mainly we use hydrogen as a source of energy. The global concern related to clean energy makes it so important to study hydrogen. So best we have hydrogen is used as fuel mainly. So studies are being developed that to use hydrogen as a fuel. Next continuation. Position of hydrogen in the periodic table. First topic we have position of hydrogen in the periodic table. So hydrogen contains only one electron, one proton. So hydrogen is the first element of the periodic table, but its position in the periodic table has been a subject of discussion for the past few years due to its similarities with both halogens and alkyl metals. So it can be placed in first group, or it can be placed in 17th group. So that's why it has similarities with both halogens and alkyl metals. That's why its place is not yet been resolved. Hydrogen is the first element of the periodic table, but its position in the periodic table has been a subject of discussion for the past few years due to its similarities with both halogens and alkyl metals. A proper position could not be assigned. This is very important. Please see here. A proper position could not be assigned to hydrogen either in the Mendeleev's periodic table or in the modern periodic table because of the following reason. First reason, in some properties it resembles like alkali metals because it exhibits +1 oxygen state. How it resembles in alkali metals? Because it exhibits hydrogen exhibits hydrogen exhibits +1 oxidation state. So that's why it can be compared with alkali metals. And in some properties it resembles halogens because with the metals it exhibits -1 oxygen state. With the metals, more electropositive metals such as sodium, with metals such as sodium, potassium, etc., sodium, potassium, magnesium, etc., it exhibits it exhibits -1 oxidation state. So valence is 1 in both the cases. So that's why it is having similarity with -1 oxygen state. So -1 oxygen state. So that's why in some properties it resembles like halogens. So hydrogen can be placed both in group 1 and group 17 with alkali metals and halogen respectively. So already we know group 1 is alkali metals and group 17 is halogen elements. So that's why it can be placed due to certain similarities of properties, either physical or chemical properties with alkali metals and and 17 group elements. That's why hydrogen place is not yet resolved till now, either in the Mendeleev's periodic table nor in the modern periodic table. So this is the position of hydrogen in the periodic table. So it's a very important discussion. Next continuation. Now coming to isotopes of hydrogen. Hydrogen has mainly three isotopes. Very very important. Hydrogen has three isotopes. What are isotopes? Elements having same atomic number but different mass number are called isotopes. Elements having same atomic number, same atomic number, but different mass number, atomic mass, or you can say mass number, are called isotopes. Are called what? Are called isotopes. So many elements in the periodic table can form isotopes. So hydrogen has three isotopes mainly. One is protium, it is 1H1. It has no neutron. In protium, there is no neutron because its configuration is 1H1, means it contains one electron, one proton, that's all. So 1H1. Second is, that is hydrogen only. Second is deuterium, 1H2. It contains neutron. It contains what? Neutron. Deuterium, and next is tritium, 1H3. So 1H1, 1H2, and 1H3. 1H3 is called tritium. Tritium is radioactive. Tritium isotope of hydrogen is radioactive. And 1H2 is deuterium. Deuterium is also heavier isotope of, and it contains one neutron only, and it contains two neutrons. Tritium contains how many neutrons? Two neutrons. That's why 2 plus 1 total mass number is 3. 1 plus 1 total mass number, 1 neutron plus 1 atomic number, that is 1 proton. So it becomes 2. So hydrogen has three isotopes, that is protium, deuterium, and tritium. These all differ from each other in respect of number of neutrons present in the nucleus. Protium does not contain any neutron. As I told you, protium does not contain any neutron. And deuterium, also known as heavy hydrogen, heavier form of hydrogen is called as deuterium, contains only one neutron, while the number of neutrons in the nucleus of tritium is 2. Tritium is radioactive and emits low energy beta particles. Tritium is radioactive and emits low energy beta particles. So these are the isotopes of hydrogen. Hydrogen has three isotopes, mainly protium, deuterium, and tritium. Tritium is a radioactive isotope of hydrogen, and deuterium is a heavier isotope of hydrogen. It contains only one neutron. And the isotope of hydrogen which do not contain any neutron is protium. Protium is 1H1. It contains no neutron. So all these 3 points are very important from this slide. So please remember, from these points also you may get a question in the examination. Next, continuation. So protium 1H1, one atomic number 1, mass number 1. It contains relative abundance is 99.99%. Very, very important, this table. Please make a note of it. And deuterium 1H2, it is containing one atomic number 1. Atomic number is same for all because it is an isotope, and mass number is 2 because it contains one neutron, and its abundance is 0.015%. And tritium is very, very less. It is rare also, you can see, rarely available. So its atomic number is 1 and mass number is 3 because of two neutrons. Here two neutrons I write, and here one neutron, and here zero neutrons, no neutrons, zero neutrons. Okay, so one neutron, two neutrons, zero neutron, and the abundance of tritium is 10 to the power of minus 18 percentage. So tritium is very rare and it is radioactive. Radioactive means it emits alpha, beta, and gamma radiations. How can you say whether an element is radioactive or not? To say whether it is an element is radioactive or not, we can have one more theory. So that we'll discuss later on. So tritium is radioactive and it emits alpha, beta, gamma radiations. It emits alpha, beta, gamma radiations when exposed to light. So that's why its state is different. So deuterium is a heavier isotope of hydrogen. So deuterium is the heavier isotope of hydrogen. Tritium is the radioactive isotope of hydrogen, and protium is a normal hydrogen. It is 99.9% abundance. So in the whole universe, hydrogen is the most abundant element because all the stars are made of comets, meteors, etc. All the heavenly bodies are made up of hydrogen only. hydrogen only. So that's why they are considered as it is uh, most abundant element in the universe, not on the Earth's crust. In the Earth's crust, it is third position. Next, coming to resemblance with alkali metals, how it is resembling with alkali metals. As we discussed, hydrogen is having similar properties with respect to alkali metals as well as halogens. So let us see in what cases it is similarity with between hydrogen and alkali metals. First, we have electronic configuration. Hydrogen contains only one electron in the valence shell, like alkali metals, because alkali metals, it is configuration is ns1. So here also hydrogen 1s1, lithium 2s1, 3s1, 4s1, 5s1. So with respect to number of valence electron, hydrogen is similar to alkali metals. Hydrogen is similar to what? Alkali metals, because alkali metals are also having ns1 configuration. Hydrogen is also 1s1 configuration. So outermost electronic configuration is 1s1. Next, coming to second point, point number 2 regarding this electropositive character. So as I told you, electropositive character, like alkali metals, hydrogen also loses only one electron to form H plus ion. Hydrogen ion, that is H plus actually. So here it is H plus, and that's why it is due to its electropositive nature. Electropositive, but exhibit an electropositive character and a monovalent. Both have tendency to lose the valence shell electron. So in case of hydrogen and more in the case of alkali metals to form unipositive ion. So the tendency is more in case of alkali metals when compared to hydrogen ion, that is H plus ion, to form unipositive ion. But still, as it is forming unipositive ion, we can say the word right here, unipositive ion. Unipositive ion means only one positive ion, like alkali metals, like sodium plus, potassium plus. But the tendency of losing of electron from alkali metals is more when compared to hydrogen. The tendency of losing electron in hydrogen is very, very less. But still, as it is forming unipositive ion, it is compared with electropositive character. As it is having electropositive character, it can be compared with alkali metal. So the second comparison, why hydrogen is compared with alkali metals. Next, third comparison, oxygen state. Like alkali metals, hydrogen exhibits an plus one oxygen state in its compound, such as HCl. In HCl, with the non-metals, it shows plus one oxygen state. With the non-metals, it shows plus one oxygen state. With water also, with the non-metals, all non-metals, hydrogen exhibits plus one oxidation state, plus one oxidation state with the non-metals. So please write this, with the non-metals. It exhibits plus one oxygen state with the non-metals. So hydrogen exhibits plus one oxygen state with non-metal. Next, reducing character. Alkali metals acts as reducing agent because as they are strongly electropositive, they act as reducing agent because of their tendency to lose electrons, to lose valence electrons. So hydrogen is also a very good reducing agent as evident from the following reaction. You can see here ferric oxide. This is called ferric oxide on reaction with hydrogen forms iron plus water, means hydrogen is displacing iron from ferric oxide. So it is a redox reaction because oxygen instead of iron is here plus 3 and here it is 0. Plus 3 to 0 reduction. So hydrogen is bringing reduction to ferric oxide, and that's why it is called as reducing agent, and itself it is getting oxidation. That is okay. Now here hydrogen is also a very good reducing agent. You can see in this reaction also cuprous oxide on reaction with hydrogen, it forms copper plus water. So here copper oxygen state is 0, copper oxygen state is plus 2 here. So plus 2 0 changes to 0. It means reduction. So hydrogen is bringing reduction to copper oxide and making it reduce to copper, and itself is getting oxidized to water. So in these two reactions, hydrogen, by using these two reactions, we can say hydrogen is acting as a good reducing agent. So that's why it is compared with alkali metals. It is compared with alkali metals. So first comparison, electropositive character. Second comparison, first comparison, electronic configuration. Second comparison, electropositive character. Third comparison, oxygen state. Fourth comparison, reducing character. That is reducing agent. So reducing character. And next fifth comparison now we are going to discuss. So these are the four different comparisons. We have similar comparisons with respect to alkali metals. Next, combination with electronegative elements. Just like alkali metals, hydrogen combines with electronegative elements such as halogens, oxygen, sulfur, etc. to form compounds with similar formula. With similar formula, so we can have, for example, halides. Halides. It is nothing but HCl, HBr, HF. and Hi. These are called halides, hydrogen halides, hydrogen halides. So like alkali metal halides, these also form hydrogen halides. Next, sulfides. So like sodium sulfide, we have alkali metal sulfide, like that hydrogen sulfide, sulfide H2S. Same formula, similar formula is because the valency of both the alkali metals as well as uh, alkali metals as well as hydrogen is same. That's why we are getting similar formula. So hydrogen halides, sodium hydride, for example, if we take sodium hydride, so that is also same. Next we have oxides. Oxides means like hydrogen, water. It contains water. So sodium oxide, potassium oxide, etc. And sulfur, halogen oxides. These are the different compounds hydrogens form. That's why the affinity for non-metals. So the combination with the electronic elements, it is similar. Just like alkali metals combines with electronic elements such as halogens. Hydrogen also combines with the same. So just like alkali metals, hydrogen also combines with electronic elements such as halogen, oxygen, sulfur, etc. to form compounds with similar formula. Example formation of halides, sulfides, and oxides. So even sodium hydride, sodium sulfide, sodium oxide. The formula is same. That is M2S, M2O, and MS. So in the same way here also you get. I hope you understood clearly. Next continuation is the fifth character. Next, before going to fifth character, we have sixth one also I write here. One more important point. Sixth point, similarity, sixth similarity. That is electrolysis. Electrolysis. Whichever is not there, I'm writing here, so please make a note. So sixth character is electrolysis. On electrolysis of aqueous solution of on electrolysis of aqueous solution of aqueous solution of on electrolysis of aqueous solution of hydrogen halides, HX, or oxides, H2O, or dihydrogen, sorry, HX and H2O. Dihydrogen is liberated at anode. What is liberated? Sorry, cathode. On electrolysis of aqueous solution of HS and H2O, dihydrogen is liberated. Dihydrogen, that is H2, is liberated at cathode. Is liberated at cathode. So this is another similarity with the alkyl metals. And similarly, alkyl metal halides. Similarly, alkali metal halides or oxides, also alkali metal halides aqueous solutions also liberate dihydrogen, that is hydrogen at cathode on electrolysis. So this is the sixth comparison. So that's why hydrogen is compared with alkali metals on based on 6 points. First point number one, electronic configuration. Point number two, electropositive character. Point number three, oxidation state. Point number four, reducing character. Point number five, affinity for non-metals or electronegative elements. And point number six, electrolysis. So just like how alkali metal halides, similarly, electrolysis is formed. So, electrolysis by the how hydrogen undergoes hydrogen halides and hydrogen oxides undergo electrolysis by giving dihydrogen is liberated at cathode. Similarly, alkali metal halides aqueous solution and alkali metal oxides aqueous solution also liberate hydrogen at cathode on electrolysis. So, these are the six similarities of hydrogen. These are the six similarities of hydrogen when compared with alkali metals. So, next continuation. Differences from alkali metals, ionization enthalpy. So how they are different from alkali metals. Now, so far we have seen the similarities. Now we are going to see the differences. First one, ionization enthalpy. Ionization enthalpy of hydrogen is 1312 kilojoules per mole, which is very high because it contains only one electron. So that's why it's very, and that electron is very close to nucleus. It is under nuclear reaction. So very high ionization enthalpy is to be given to hydrogen atom. Then only it can lose one electron. So ionization enthalpy of hydrogen is 1312, that is 1312 kilojoules per mole, is very high in comparison with ionization enthalpy of alkali metal. That is the first difference. Second difference, existence of H minus ions. Since already I told you, hydrogen also exhibits minus one oxygen state. It has been established that H minus ion does not exist freely in aqueous solution. This is because of the fact that it has a very small size compared to normal atomic and ionic size. H plus, I'm sorry, this is H plus and this is H plus. Existence of H plus ions is not freely in aqueous solution. This is because of the fact that it has a very small size as compared to normal atomic and ionic size, which ranges from 50 to 220 picometers. Thus, it exists in aqueous solution only in the form of hydrated proton with the formula of H9O4 minus. How will this H9O4 minus came? H plus when combines with water, it forms H plus when combines with water, it forms H3O plus. This H3O plus combines with further water and forms H plus, combines with H3O plus and forms H9O4 plus. This is plus. So that's why it exists in solution form as H9O4 plus. However, for the sake of simplicity, the hydrated proton is represented as H3O plus. As I told you, the hydrated proton is represented by hydronium ion, that is H3O plus. This is H3O plus. On the other hand, the alkali metal ions mostly exist as hexahydrated ions. Hexahydrated ions means like alkali metal ions, for example, LiCl2.6H2O. So it forms hexa. Hexa means 6 water molecules, hexahydrated ions. So that is another dissimilar, that is existence of H plus. Existence of H plus is not present directly independently because of its small size, whereas existence of Na plus alkali metal ions is present because Na lithium plus is present, Na plus is present, and so on. So existence of alkali is present, whereas alkali metal ion is present, whereas H plus ion is not present independently. This is because of the fact that it has a very small size as compared to normal atomic and ionic size, which ranges from 50 to 220 picometers. Thus, it exists in aqueous solution in the form of hydrated proton with the formula H9O4 plus. However, for the sake of simplicity, hydrated proton is represented as H3O plus. How this H3O plus has come? H plus combines with water and forms H3O plus. This is called hydronium ion. This is called what? Hydronium ion. On the other hand, the alkali metal ions exist as hexahydrated ions. Example, NaCl2.6H2O. So these are the main differences between hydrogen and alkali metals. Next continuation. Now differences in halides. And one more important point I want to add here. One more difference. Hydrogen exists as diatomic gas. Hydrogen exists as diatomic gas because H2 gas. Whereas alkali metals are solids. This is also one more difference. Whereas alkali metals, alkali metals are solids. So this is one more difference, that is physical appearance. And ionic radii of H plus ion is just even ionic radii, ionic radii of H plus ion is less when compared to alkali metals. When compared to alkali metals. So these are the main differences of alkali metals with hydrogen. Now we'll see difference in the halides. Hydrogen halides are different from the halides of alkali metals, though they have similar molecular formula. For example, pure HCl is covalent compound, while NaCl is ionic compound. HCl is a gaseous compound, while NaCl is a solid at ordinary temperature. So these are the differences of halides. Differences between hydrogen and alkali metals. Differences between hydrogen and alkali metals. So total how many points we have? Ionization enthalpy, difference in the physical state, ionic radii, nature of oxides, nature of halides. Nature of halides also. Hydrogen halides is a covalent compound, while NaCl is an ionic compound. HCl is a gas compound, gaseous compound, while NaCl is a solid compound at ordinary temperature. And oxides of hydrogen is neutral, while those of alkali metals are basic. In this also you can add oxides of hydrogen. Oxides of hydrogen are neutral. Example water, whereas whereas alkali metal oxides are basic in nature. Alkali metal oxides are basic in nature. So these are the dissimilarities between alkali metals and hydrogen. These are the dissimilarities. How many dissimilarities we have? Nature of halides, nature of oxides, ionic radii, difference in the physical state, ionization therapy. Total 5 differences. I hope all these 5 differences are important because they can ask statement-based question from these 5 differences. Next continuation. Resemblance with halogens. So next concept is how they have similar with halogens. First, electronic configuration. Just like halogens, hydrogen needs one electron to attain stability for the configuration of new noble gas for attaining stability. Next, atomicity. Halogens are diatomic. Similarly, hydrogen is also existing in a diatomic molecule. All the halogens, chlorine, bromine, iodine, they exist as diatomic molecules, and moreover, they are gases. The atomicity of hydrogen as well as halogen is 2. Atomicity means number of atoms per molecule. Number of atoms per molecule is called as atomicity. The atomicity of hydrogen as well as halogens is 2, same. Next, electrochemical nature. During electrolysis of lithium hydride, calcium hydride, etc., in molten state, hydrogen is evolved at the anode, indicating its electronegative nature. In this aspect, hydrogen shows resemblance with halogens, which are also liberated at the anode during electrolysis. All the halogens are all the halogens, all the halogens are obtained at anode in the electrolysis treatment, in the electrolysis process. Next, oxygen state. Just like halogens, hydrogen also exhibit -1 in some of the compounds such as metal hydrides. Metal hydrides, strongly metallic hydrides like sodium hydride, it is +1 and this is -1. Potassium hydride KH, it is +1 and it is -1, and so on, etc. So with respect to metallic hydrides, like just like halogens exhibit -1 oxygen state, hydrogen also exhibit +1, -1 oxygen state. These are the important similarities with halogens. Next continuation. Combination with alkali metals, like how halogens combine with alkali metals, like that hydrogen also combines with alkali metals, such as it forms sodium hydride, sodium chloride, lithium hydride, lithium chloride, calcium hydride, calcium chloride. So how halogens are combining with metals, same way hydrogen also combines with metals. In all these metallic hydrogen hydrates, the oxygen state of hydrogen is -1, -1, and -1, and chlorine is also -1. That's okay. So hydrogen exhibits -1 oxygen state also with metals. These are called as metallic hydrides. These are called what? Metallic hydrides. What do you call them? They are called as metallic hydrides. Combination with non-metals. Just like halogens, hydrogen also react with non-metals such as carbon, silicon, germanium, etc. to form covalent compounds. For example, hydrogen combines carbon and forms, see here. So just like halogens, hydrogen also react with non-metals. Non-metals with respect to such as carbon. So with carbon, hydrogen combines with carbon and forms CH4. It forms methane, like that. So hydrogen combines with oxygen and form water. Hydrogen combines with oxygen, 2H2 plus O2 gives H2, 2H2O. So they form covalent compounds. All these are covalent compounds. With silicon, it forms silicon hydride. Si plus 2H2 forms SiH4, silicon hydride, that is SiH4. Similarly, with germanium also it forms germanium hydride, GeH2. So all these compounds, that is methane, water, and silicon hydride, are covalent in nature. They are covalent compounds, and even halogens also combines with non-metals to form covalent compounds, just like halogens. For example, carbon, when combines with chlorine, it forms carbon tetrachloride, CCl4. So this is also a covalent compound. So carbon, when combines with oxygen, forms carbon dioxide. It is also a covalent compound, like that. So halogen also, halogens combines with halogens combines with non-metals, as well as hydrogen also combines with non-metals. So this is again this is similarity between halogens and hydrogen. This is the sixth similarity. Next, ionization energy. Ionization energy of hydrogen is comparable to the ionization energy of halogens. This point is very important. The ionization energy of hydrogen is comparable to the ionization energy of halogen as shown below. Ionization energy of hydrogen, here hydrogen is 1312, that is 1312 kilojoules per mole. Flow unit is 1681, greater than that. Flow unit is almost similar, and bromine is very near. So the ionization energy of hydrogen is comparable to the ionization energies of halogens as shown below. So this is another similarity. And moreover, next, now we'll see. So these are the eight similarities, seven similarities we have, mainly main similarities we have: atomicity, oxygen state, affinity for metals, affinity for non-metals, liberation at anode, and ionization enthalpy. These are the eight similarities we have. Next, we have differences between halogens. In what way they are different? Mainly three. First, less tendency of hydride. First difference is formation of, although hydrogen forms hydride ion, H plus ion like halogens, yet its tendency to form hydride ion is very, very less in comparison with the halogens. It is quite clear from that fact that halogens form halides with very large number of metals, but hydrogen forms hydrates only with small number of metals like sodium and calcium, etc. Only with first, second group elements only it forms hydrates, whereas halogens can form halides with almost all the metals, like even zinc, copper, etc. But hydrogen cannot form hydrates with zinc, copper. So zinc hydride does not exist, does not form. Copper hydride does not form. So that's right. Hydrogen can form hydrates only with alkali metals and alkali earth metals. That is first group and second group metals only it can form hydrates. First group and second group metals only. Hydrogen can form hydrates. Hydrates can form. Hydrates are formed mainly. The third group aluminum hydride does not exist. It exists as dimer. So this is the less tendency of hydrate formation. Less tendency of hydrate formation. Whereas halogens have the more tendency of hydrate formation. Whereas hydrogen does not have more tendency to form hydrates. Only with exceptions like first group and second group metals only it forms hydrates. Remaining all other metals it will not form hydrates so easily. So there is a less tendency of hydrate formation. That is the first dissimilarity. Next, also electronic configuration. Unlike halogens, hydrogen contains only one proton and no neutron in its nucleus, and only one electron in the extranuclear part. Continuation. Next, nature of oxides. The oxides of halogen are acidic. Very important point. The oxides of halogens are acidic in nature, whereas oxide of hydrogen is neutral. So, example, water is neutral, whereas halogen oxide, that is Cl2O7, is acidic, highly acidic. So the oxides of halogen are acidic, whereas oxide of hydrogen is neutral. Oxide of hydrogen is what? Neutral. Nature of compounds. The compounds of hydrogen with halogens, that is hydrogen halides, are low boiling covalent compounds, whereas alkali metal halides are high melting ionic solids. So this is again nature of compounds. They are having defensive. And one more, electronegativity. Electronegativity of halogens is high. These are the dissimilarities we are discussing now. Electronegativity of halogens are very high when compared to hydrogen, are very high when compared to hydrogen, when compared to hydrogen gas. Similarly, so hydrogen has less tendency to gain electron and form uninegative H minus ion, whereas halogens have strong tendency to form halide ion. So they have electronegativity of halogens are very high when compared to hydrogen. And moreover, electronic configuration. In electronic configuration, hydrogen has no neutron. Electronic configuration, that is also one more dissimilarity. Hydrogen has no neutron, no neutron, whereas halogen has neutrons. Halogens has neutrons. So these are the dissimilarities between hydrogen and halogen. So what are the main dissimilarities? Electronic configuration, electronegativity, nature of compounds, nature of oxides. Total four differences. So nature of compounds and nature of oxides. So these are the dissimilarities of hydrogen with halogens. Hydrogen with halogens. Next, continuation. Now conclusion. From the above discussion, it is quite evident that there is a marked resemblance in the properties of hydrogen with alkali metals as well as with halogens. Therefore, it is very difficult to place it either with the elements of group 1 or those of group 17. In other words, position of hydrogen in the periodic table is anomalous. It is due to this reason hydrogen is sometimes called as rogue element. Why it is called rogue element? Because of its resemblance with halogens. So its position is not at all fixed so far. So that's why it is also called as rogue element. Rogue element because there is no fixed position due to no fixed position in the periodic table. No fixed position in the periodic table. So these are the main conclusions from this hydrogen. Now we'll move to next concept, preparation of dihydrogen. So next we have dihydrogen. Hydrogen is the most abundant element in the universe. 70% of the universe is total mass because the giant planets, namely Jupiter, Saturn, consisting of only hydrogen, about half of the mass of the sun and other stars is made up of hydrogen. So it is the third most abundant element in the surface of the globe, but is the most abundant in the universe because hydrogen is the most abundant element in the universe. Why? Because it occupies 70% of universal mass. How much percentage? 70% of universal total mass. Hydrogen is the most abundant element. It consisting of 70% of universe. So 70% of universe total mass is nothing but hydrogen only. Now we are going to do preparation of dihydrogen. So occurrence hydrogen we already know. So dihydrogen is not found in our atmosphere as hydrogen molecules are very light and the earth does not possess gravitational pull to retain them. So dihydrogen is not found in our atmosphere as hydrogen molecules are very light and the earth does not possess gravitational pull to retain them. Now coming to preparation of dihydrogen. So isotopes of hydrogen also we have learned. So relative abundance of isotopes of hydrogen also we have learned. Now preparation of dihydrogen. So the main sources for which dihydrogen can be prepared are water, acids and alkalis. So main source of preparation of hydrogen dihydrogen are from water, comma, alkalis, that is soluble bases, and acids. From these three, we can prepare a dihydrogen. So, some of the important methods of preparation of dihydrogen are given below. By the action of water on metals. First preparation by the action of water on metals. Various metals react with water at different temperatures to displace hydrogen from it. For example, very active metals like sodium, potassium, calcium react at room temperature to form hydrogen along with corresponding hydrides, and the reaction with these metals is highly vigorous and hydrogen liberated immediately catches fire which can cause accident. In order to slow down the reaction, amalgam of these metals with mercury are used. Very important point. So I'll write the equations now. You can just see here. So water at ordinary temperature. So first reaction, sodium on reaction with water, it forms sodium monoxide, sodium hydroxide, sodium hydroxide along with hydrogen gas. Second example, this is first example. Second example I'm giving, calcium on reaction with hydrogen with water, it forms calcium hydroxide along with hydrogen gas. So these two molecules, calcium hydroxide along with hydrogen gas. This is the second preparation. So water at ordinary room temperatures. Metals having very low standard of reduction potential, like alkali metals and alkaline earth metals, combines with hydrogen, combines with water. So metals, very active metals like sodium, potassium, calcium react at room temperature with hydrogen to form hydrogen along with corresponding hydroxides. So example, sodium hydroxide, calcium hydroxide, potassium hydroxide, magnesium hydroxide, etc. with boiling water. So normal room temperature and with boiling water, with boiling water, which metals will form? I'll just show you now here. Please note it down. Magnesium, zinc, and aluminium. Magnesium, comma, zinc, and aluminium combines with boiled water and forms hydrogen gas and liberates hydrogen gas. So, example, magnesium on reaction with hydrogen gas or with water, boiling water, it forms magnesium hydroxide plus hydrogen gas. Magnesium hydroxide MgO is taken twice plus hydrogen gas. So it is nothing but 2 moles of water. So like this equations are important. So first reaction, preparation of hydrogen by the action of water on metals. So various metals react with water at different temperatures to displace hydrogen from it. For example, very active metals like sodium, potassium, calcium react at room temperature to form hydrogen gas along with corresponding hydroxides. Example, sodium combines with water and forms room temperature. It forms sodium hydroxide and hydrogen gas. Calcium combines with water at room temperature and forms calcium hydroxide and hydrogen gas. Whereas coming to magnesium and zinc and aluminum, in the case of magnesium, zinc and aluminum, they also come in with boiling water. The difference is what? Boiling water. Here I write here boiling water. So boiling water and forms magnesium hydroxide along with hydrogen gas. Zinc also combines with boiling water and forms zinc hydroxide along with hydrogen gas. Aluminum also combines with boiling water and forms aluminum oxide along with hydrogen gas. With aluminum, it forms not oxide, it forms. So aluminum combines with water, boiling water, and forms aluminum oxide, not aluminum hydroxide, forms aluminum oxide Al2O3 plus hydrogen gas, that is hydrogen gas. So in this way, aluminum combines with water and forms Al2O3 and hydrogen gas. So this is the preparation, first preparation of dihydrogen, and the reaction with these metals, that is sodium, calcium, and potassium. Sodium, calcium, and potassium. Reaction with these metals is highly vigorous, and hydrogen liberated immediately catches fire. The hydrogen liberated from these two equations, which catches fire and can cause accident. So, in order to slow down, these reactions are done among amalgam of these metals are with mercury are used. Amalgam means sodium with mercury, that is sodium amalgam. Sodium amalgam combines with water. So calcium amalgam, CaHG, combines with water and so on. So amalgam is used to prevent that fire. So this is the first preparation of hydrogen. First preparation of hydrogen. All these points you have to make a note in your classwork, then only you can understand. Otherwise, it's very difficult to understand. So please make a note of all these points. Next continuation. Second preparation. Let us see now second preparation. Metals like magnesium, aluminum, zinc, etc. react with water at boiling temperatures only to form hydrogen gas and corresponding oxides. As I told you, magnesium, aluminum, zinc combines react with water at boiling temperatures to form hydrogen and corresponding oxides. Next, third one, metals like iron, metals like iron, tin, etc. react with steam at high temperature. So iron combines with steam. This is the steam form and forms iron oxide, that is ferric oxide plus hydrogen gas. So the reaction between iron and steam is used for the large scale preparation of dihydrogen by Lines process. So this is the commercial preparation of hydrogen, and the reaction is also reversible. So this reaction, that is 3Fe plus 4H2O, gives rise to Fe3O4 plus 4H2, that is ferric oxide plus 4 moles of hydrogen gas. This reaction is reversible, and that's why it is used as, whereas this reaction is reversible and it is steam only with high temperature, that is such as iron, nickel, and tin. With the nickel also, with the tin also, nickel also in the same reaction, tin also the same reaction. It forms their respective oxide. So iron, nickel, tin does not combine with cold water or boiling water. It combines only with steam. Here this is called steam, only vapor, water vapor. So this the reaction between iron and steam. So this reaction is used for the large scale preparation of dihydrogen by Lines process. So this is the third preparation of hydrogen. Next continuation. So please make a note whatever reactions are not there I'm writing. Next, next reaction by the action of acids on. So by the action of acids on metals, metals lying above hydrogen in the activity series, you know electrochemical series. So this is called activity series, is also called as electrochemical series, which this series Based on this series, we'll give one chart like it. So this electrochemical series we'll be discussing in 12th class. So just listen now. Metals lying above hydrogen in the activity series, that is electrochemical series, displace hydrogen by the reaction with dilute HCl or dilute sulfuric acid. So for example, sodium metal or aluminum metal, zinc metal. So for example, zinc on reaction with sulfuric acid, it forms zinc sulfate along with hydrogen gas. Similarly, iron on reaction with HCl, it forms 2 moles of HCl. It forms FeCl2, is FeCl3 or FeCl2 plus hydrogen gas. So, what is the statement now here? Metals lying above hydrogen in the activity series displace hydrogen by the reaction with dilute acid, dilute HCl or dilute sulfuric acid. So, not only this, any metal you can take, sodium also, sodium on reaction with hydrogen sulfuric acid and forms dilute sulfuric acid, it forms sodium sulfate, Na2SO4 plus hydrogen gas. So all the metals lying above hydrogen in the activity series, that is from lithium till copper. Copper will not go from this. So lithium till copper. So all the metals lying above hydrogen in the activity series on reaction with dilute acids, liberate hydrogen gas, that is dihydrogen gas. In the laboratory, dihydrogen is prepared by the action of treatment of zinc granules with dilute sulfuric acid. So this is the lab preparation of hydrogen gas, that is zinc granules on reaction with dilute sulfuric acid form zinc sulfate along with hydrogen gas. So this method is also called as laboratory preparation of hydrogen gas. Next, by the action of strong alkalis and metals like zinc, tin, or aluminum react with strong alkalis such as sodium hydroxide or potassium hydroxide liberating hydrogen gas. So zinc reacts with sodium hydroxide, that is strong alkali, and forms sodium zincate Na2ZnO2 plus hydrogen gas. So this is 2 moles of NaOH. So Na2ZnO2. Similarly, beryllium, sodium, tin, everything. So zinc, tin, aluminum react with strong alkalis, aluminum. So aluminum combines sodium hydroxide, NaOH, and forms aluminum combines sodium hydroxide and forms sodium metaaluminate, Na2AlO2, Na2AlO2, and with the liberation of 3 moles of hydrogen gas. So balancing and all you can do. So zinc combines sodium zincate, aluminum zincate, sodium stannate. With tin also it forms sodium stannate plus hydrogen gas. So by the action of strong alkalis and metals, this is metals like metals like zinc, tin, aluminum react with strong alkalis such as sodium hydroxide, potassium hydroxide, liberates hydrogen gas. So this is the third preparation. This is the third preparation. Next continuation. So now we are dealing with preparation of hydrogen, dihydrogen. Next we have electrolysis of water, very, very important. Hydrogen is also prepared by the electrolysis of water. So commercial preparation of hydrogen is nothing but by the electrolysis of water. This is also called as commercial preparation of hydrogen. Commercial preparation of hydrogen gas by the electrolysis of water. By the electrolysis of water. So dihydrogen with high degree of purity is prepared by the electrolysis of water. There is a small amount of acid or base. So a small amount of acid, that is like sulfuric acid. Let us take sulfuric acid. A small amount of sulfuric acid or an alkali, example sodium hydroxide, or an alkali, that is sodium hydroxide. Small amount, that is 15 to 20%, is added to water. That is 15 to 25% is added to water. Is added to water and electrolyzed in a cell in which iron sheet is used as. In this, iron is used as iron sheet. Iron sheet is used as cathode and nickel plated iron sheet. Nickel plated iron sheet is used as anode. Iron sheet is used as cathode and nickel is used as anode. So it is used as anode. Now, what happens at cathode? So addition of acid and alkali to water molecules makes a good conductor of electricity. By we are adding addition of small amount of sulfuric acid and sodium hydroxide to water, small amount of sulfuric acid and sodium hydroxide to water, because it improves the conductivity of water. So it makes a good conductor of electricity. The anode and cathode are separated by means of porous asbestos diaphragm. So electrolysis. So what happens here? So here what happens at cathode? H2O on electrolysis forms H plus and OH minus ions. H plus and OH minus, and because we are adding only small amount of sulfuric acid and sodium hydroxide. Why we are adding small amount of sulfuric acid and sodium hydroxide to water? To make it conductible, so that electricity is easily passed through water, to make it conductible. So that's why we are adding. So when you take aqueous solution of water, what will happen? On electrolysis, it forms H plus ions and OH minus ions. These H plus ions goes to cathode. At cathode, gains one electron and forms hydrogen gas. So 2H plus ions gains 2 electrons and forms hydrogen gas at cathode. At cathode, what is formed? Hydrogen gas. And at anode, so OH minus ions. So these four OH minus ions, this is 2H2O. So we can say 2H2O, 4 OH minus. So we can say these four OH minus ions at anode becomes 4 OH plus 4 electrons, that is 2H2O plus 4 electrons, which changes to 2H2O, 2 moles of water plus 1 mole of oxygen gas is formed at anode. So at anode, oxygen is formed, at cathode, hydrogen is formed. So at cathode, hydrogen gas is formed, at anode, oxygen is formed. So this is called commercial preparation of hydrogen gas, that is dihydrogen, by the electrolysis of water. This is very, very important. Dihydrogen of high degree of purity is prepared by the electrolysis of water in the presence of small amount of acid or base. Why we are adding 15 to 25% of small amount of acid or base to water? To make it conductible. Very, very important point. And in this electrolysis process, iron is taken as cathode and nickel is taken as anode. And this water, on passing current, what happens? Water dissociates to form H plus and OH minus ions. This H plus ions goes to cathode by gaining electrons and forms hydrogen gas at cathode, and OH minus ions by losing electrons forms water and oxygen gas at anode. So at cathode, hydrogen is formed, and at anode, oxygen gas is formed. So this is nothing but the commercial preparation of manufacture of dihydrogen gas. I hope it is clear. Very, very important. So why the small amount of acid or base is added to aqueous solution, that is water, or the electrolysis of water to prepare hydrogen gas? Because water is not conductible. So to make water a good conductor of electricity, we'll add small amount of sulfuric acid or sodium hydroxide, strong alkali, strong acid. We'll add up to 15 to 25% is added to water, so that to make it good conductor of electricity or to make it conductible. To make the solution good conductor of electricity, we'll add these two. So this process is called as hydrolysis, electrolysis of water, that is preparation of hydrogen by electrolysis of water, and is also called as commercial preparation of hydrogen gas. Commercial preparation of hydrogen gas, very, very important. So this is called preparation of hydrogen gas commercially. Next continuation. So please make a note of all this. That diagram is not important. The points which we have discussed is very important. So next, laboratory preparation of dihydrogen. You can see here in the lab how it is prepared. Dihydrogen is prepared by the action of dilute sulfuric acid on granulated zinc, that is zinc granules. These are called zinc granules, and as shown in the figure. So this is taken here. What is taken here? This is flask is taken. This round bottom flask is taken, and further it is connected to water. So what happens? So granulated zinc, according to the arrangement as shown figure. So it can also be prepared by the reaction of zinc with aqueous alkali. So aqueous alkali is taken here. So zinc on reaction with sulfuric acid or sodium hydroxide. Zinc on dilute sulfate also. Zinc on reaction with dilute sulfuric acid also. It forms zinc sulfate plus hydrogen gas. So this is also laboratory preparation, and that is also with alkali also we can prepare. So in the lab we can prepare hydrogen by using this and that. So that is either zinc sulfate, sorry, sulfuric acid or sodium hydroxide. It can also be prepared by the reaction of zinc with aqueous alkali. So zinc along with the acid is taken in the round bottom flask. Then what happens? It forms zinc sulfate solution, and hydrogen gas is collected in the by the downward displacement of water. Here I write here hydrogen gas being lighter, being lighter is collected. Hydrogen gas being lighter is collected by the downward displacement of water. What is this? Downward displacement of water. So here you can see downward displacement of water, hydrogen gas is collected. So that lighter gas will come up. So due to this, on the surface of water, hydrogen gas is formed. In this way, we can connect it. So in the laboratory method, we have preparation one. In the lab, we have two preparations. First is zinc on reaction with dilute sulfuric acid and zinc with on reaction with alkali. So with alkali also, it forms sodium zincate. This is called what? Na2ZnO2. This is called Na2ZnO2. It is called sodium zincate. What it is called? Sodium zincate. So this is the preparation of dihydrogen in the commercial places as well as lab. Next continuation. Bosch process. Very, very important. The maximum quantity of commercial dihydrogen is prepared by this method. It involves the following steps. Preparation of water gas first, and second one is prepared by the action of steam with red hot coke. So first one, how water gas is prepared. Water gas can also be obtained by the action of steam on hydrocarbons in the presence of catalyst. This process is also called as steel reforming of hydrocarbons. So how does it forms? Steam on red hot coke. So carbon plus water, red hot coke. Sorry here. Carbon red hot plus steam combines together to form CO plus H2. This is called a combination of carbon monoxide and water hydrogen gas. It is also called as syngas or water gas. Water gas or syngas. This is first step, preparation of water gas. Water gas can also be obtained by the action of steam on hydrocarbons. So steam on hydrocarbons such as methane. So CH4 plus O2, sorry, CH4 plus water, it forms CO plus H2. So carbon monoxide and water gas. So this is nothing but syngas. So water gas can be also obtained by the action of steam on hydrocarbons in the presence of catalyst, in the presence of catalyst like platinum or silver or gold. This process is also called steel reforming of hydrocarbons. Steel reforming of hydrocarbons. Next, separation of hydrogen. So first step we have got hydrogen plus carbon monoxide, that is called water gas or syngas. The second step, the water gas found by any of the above methods is mixed with steam and passed over ferric oxide Fe2O3. It is passed over ferric oxide. So and chromium oxide, that is Cr2O3 at 770 kelvins, where CO is oxidized to CO2 and gas mixture of CO2 and H2 is then bubbled into cold water under pressure when carbon dioxide dissolves, leaving behind dihydrogen gas which escapes out. This reaction is called as water gas shift reaction. Very, very important. Water gas shift reaction. I'm writing here on the board. Please make a note. So water gas shift reaction. So first step we have got what? Carbon monoxide plus hydrogen gas. Next, we have water gas shift reaction. So how does water gas shift reaction takes place? So this water gas, that is CO plus H2, combines with H2O, water, in the presence of FeCrO4, that is the catalyst, FeCrO4, and forms CO2 plus 2H2, CO2 plus 2H2 gas. So iron chromate at 673 kelvins or 770 kelvins. So carbon monoxide plus water gas, this is called water gas, combines with steam. So gases mixture is passed over heated Fe2O3 and mixed with steam. So this is called steam and is passed over Fe2O3 and Cr2O3. From these two, we got FeCrO4, that is ferrous chromate, that is ferric chromate, which gives out carbon dioxide gas and hydrogen gas. So the mixture of carbon dioxide and hydrogen gas, the mixture is the gaseous mixture of carbon dioxide and hydrogen gas is then bubbled into cold water under pressure. When carbon dioxide dissolves, leaving behind dihydrogen gas which escapes out. This is called water gas shift reaction. So this is called water gas shift reaction. What is the water gas shift reaction? Again, I'm writing here. So please make a note. Water gas shift reaction. If it is not clear, I'll write it here. Entire reaction. Please make a note. So I'm working here and writing neatly because this reaction is very important. So water gas shift reactions. First to syngas formation of water gas is very important. So this is the first reaction. Second reaction, what happens? This water gas, that is CO plus H2 combination, combines together, is passed over steam, that is water, this is called steam, in the presence of catalyst, is passed over heated Fe2O3 and Cr2O3. So Fe2O3 and Cr2O3, even if you write like this also it's okay. So Cr2O3, and it forms, that is nothing but by a combination of these two, FeCrO4, that is iron chromate is formed. So this, when this water gas is passed, is mixed with steam and is passed over ferric chromate, it forms carbon dioxide gas along with water hydrogen gas, so this reaction, the second reaction, is called water gas shift reaction. Water gas shift reaction, very very important. So the above reaction is called as water gas shift reaction. So what is water gas shift reaction? So water gas on reaction with steam, water gas on combining with steam is passed over Fe2O3, heated Fe2O3 and Cr2O3 at 770 kelvins. 770 kelvins, the temperature also I'm writing here, and forms carbon dioxide gas and hydrogen gas. So, and the carbon dioxide and hydrogen gas mixture is then bubbled into cold water. So this mixture is then bubbled into cold water. This water gas shift reaction is then bubbled into cold water under pressure when carbon dioxide dissolves in it, leaving behind dihydrogen gas which escapes out. So this is called as preparation of dihydrogen by Bosch process. Very, very important. This process is very, very important. So please make a note. So this is called preparation of dihydrogen by using water gas shift reaction. Water gas shift reaction, very, very important. So next. So with this, I'm ending this session. The other session will come up with some more properties of hydrogen and new topic in this concept. So very, very important this session. Isotopes are important. Preparation of dihydrogen is also important. Water gas shift reaction, which we have discussed last, is also very important. So with this, I'm ending this session, and the next session we'll discuss with a new topic. Thank you all.